Constant current LED driver with programmable PWM control. Allegro Microsystems. Welcome to this training module on Allegro Microsystems constant current LED driver with programmable PWM control. This training module introduces the 3-channel constant current LED driver family, its internal functions and features, and some design considerations. The A6280 and A6281 LED drivers from Allegro Microsystems are 3-channel constant current LED driver ICs with programmable PWM brightness control. These devices are ideally suited to driving clusters of red, green, and blue LEDs in applications where a cluster forms a single pixel, as in large displays or lighting fixtures. It precisely controls LED brightness via 10-bit pulse width modulation per channel, complemented by 7 bits analog current control per channel to adjust color balance. The LED drivers are designed to minimize the number of components needed to drive LEDs with large pixel spacing. A large number of these devices can be daisy-chained together and controlled by 4 control signals: clock, serial data, latch, and output enable. Each of these devices is buffered to drive the next chip in the chain. The LED drivers have 3 10-bit registers to store brightness data of the PWM signal for each LED and a 31-bit shift register that loads data through the serial data input pin. All the internal latched registers are loaded by this shift register. The LED drivers also have a built-in linear regulator that eliminates the need for a chip supply bus and external voltage regulators. The driver is designed to allow daisy chaining many drivers together. Internal output buffers allow data signals to travel long distances through strings of LED drivers without needing extra driving hardware. The LED driver has a 31-bit shift register that loads data through the serial data input pin. The shift register operates on a first-in, first-out method. The most significant bit, bit 30, is the first bit shifted in, and the least significant bit, bit 0, is shifted in last. The serial data is clocked by a rising edge of the clock input pin. The serial data output pin is updated to the state of bit 30 on the falling edge of the clock input pin. This will prevent any race conditions and erroneous data that might occur while propagating information through multiple LED drivers that are daisy-chained together. The contents of the shift register will continue to propagate on every rising edge of the clock input pin. The information in the shift registers is latched on the rising edge of the latch input pin. The latch input pin must be brought low before the rising edge of the next clock pulse to avoid latching erroneous data. The latched data remains latched on the rising output enable in signal. This LED driver family is designed to allow daisy chaining many LED drivers of the same family. Clock, data, latch, and output enable signals are passed from one A6820 to the next without any loss of data due to duty cycle skewing or signal degradation. Output buffers drive data signals enough for long distances without needing extra hardware. The device drives TTL levels. Each driver input has a corresponding buffered output. The clock out pin is driven by an internal one-shot circuit. The one-shot solution produces a constant clock signal throughout the entire driver chain to ensure synchronization of the data line. This driver family controls the intensity of each LED by pulse width modulating the current of each output. It has 3 10-bit brightness registers, one for each output. These brightness registers set the PWM count value at which the outputs switch off during each PWM cycle. Each 10-bit brightness register gives 1023 levels of light intensity. From the table shown, when the brightness register is set to 0, the outputs remain off for 0% DC. When a brightness register is set to 1023, the corresponding LED remains on 100% DC as long as the output enable input is active and the PWM cycle has started. The PWM counter increments from 0 only when the output enable input pin is held low. The counter resets to 0 on a rising edge of the clock input when output enable in is high. The overall maximum current is set by the external resistor REXT connected between the REXT and logic ground pins. Once set, the maximum current remains constant regardless of LED voltage variation, supply voltage variation, temperature, or other circuit parameters that could otherwise affect LED current. The relationship of the value selected for REXT and I out is shown in the figure. The LED driver family can further control the maximum output current for each output by setting the 3 7-bit dot correction registers with scale data that ranges from 36.5% to 100% of the overall maximum output current that is set by the REXT resistor. This feature is useful because not every type of LED, red, green, or blue for example, has the same level of brightness for a given current, and the brightness could be different even from LED to LED of the same type. By scaling the output currents so that all the LEDs have matched intensities, the application will have full color depth when using the PWM counters. When the junction temperature of the LED drivers reaches the thermal shutdown temperature threshold, the outputs will shut off until the junction temperature cools down below the recovery threshold. The shift registers and output latches will remain active during the TSD event. Therefore, there is no need to reset the data in the output latches. The LED driver has an internal undervoltage lockout circuit to disable the driver outputs in the event of logic supply voltage dropping below a minimum acceptable level. This prevents the display of erroneous information, a necessary function for some critical applications. The shift register will not shift any data in under a low voltage lockout condition. Upon recovery of the logic supply voltage and on power up, the internal shift register and all latches will be set to 0. The voltage on the outputs should be kept in the range of 1 to 3 volts. If the voltage goes below 1 volt, the current will begin to roll off as the driver runs out of headroom. At Vout above 3 volts, the power dissipation may become a problem. The series resistors can be added to dissipate the extra power and keep the output voltage within the recommended range. These LED drivers can be used in large numbers to drive many LEDs with control signals connected together serially using short cables between each pixel, as shown in the diagram. Because the negative edge of the clock drives the data to the serial data output pin, and the clock output pin is driven by a 100 nanosecond one-shot function, the clock and data signals remain synchronized from the first pixel in the chain to the last. After all the data is written to each LED driver in the chain, the data is latched by each driver via a low to high transition on the latch input pin. The latch output pin of pixel 1 drives the latch input pin of pixel 2, and so on down the chain. These signals are buffered and driven asynchronously relative to the clock input and serial data input pins. Therefore, the mismatch in delays between the clock output and latch output must be taken into consideration.